What's up, guys? Today we'll be going over one of my favorite topics in physics, magnetism. Magnetism is defined as a phenomenon produced by the motion of electric charge resulting in the attractive and repulsive forces between two objects. Now today we'll be using this cylinder here, which is a non-magnetic object, placing it into Today we'll be using this non-magnetic cylinder, placing additional Today we'll be working with this non-magnetic cylinder, and by adding I'm gonna get it right. Don't even into it. Let me know. 3, 2, 1.
Go ahead.
Today we'll be using this non-magnetic cylinder, and we'll be adding a neodymium magnet to it. And when added to the cylinder will take on the properties proportional to the neodymium magnet. This process is known as paramagnetism.
Our experiment today is involved with finding the field on axis of a cylindrical magnet. So B, which is the magnetic field, is equal to BR, which is the Römnitz field, divided by 2, all multiplied to B, which is the thickness, plus Z, which is the distance from the pole of the face, divided by the square root of the radius squared plus B plus Z squared, minus Z divided by the square root of R squared plus Z squared. So this diagram right here is what our cylinder is going to look like.
So now to plug in the numbers and find our magnetic field on the axis of the cylinder, we're just going to be plugging in the numbers. So the type of magnet we used was a neodymium magnet with the magnetic being 52. The distance from a pole, we just arbitrarily chose 1 millimeter. Thickness, 47.5 millimeters, and a radius of 6.25. Now plugging all of this in into this equation, our Römnitz field of the magnet divided by 2 times d plus z, radius squared plus d plus z squared minus z over r squared plus z squared, we get our magnetic field on the axis of 21.6737 millitesla.
All right. So as we start with the experiment, we have this metallic cylinder right here. And so when we apply the magnet on it, the cylinder gets magnetized. It gets paramagnetized actually, producing magnetic fields that goes like that from both sides, from the poles of the cylinder. We actually can't tell which pole is north, which pole is south right now, but when we put the ferric solution, the ferric liquid, we actually see spikes coming out on the direction of the magnetic field. So you have the magnetic field lines like that. That's upward drawing. So you see the spikes going out like that from the ferric liquid, showing exactly where the magnetic field lines are, as will be shown in the video next.
Guys, not boring stuff over. Do some experiments. So what I got here is a little bit of ferrofluid. What this is basically a bunch of liquid magnetic fluid stuff. Nope. This stains a lot. I mean, look at this. It won't come off. That's why I'm wearing gloves. So this is our little metal cylinder right down here. If you want to take a little closer look at it. What we're going to do is I'm going to show you the magnetic field that's coming off. So this ferrofluid is going to do is going to follow the magnetic field of this little cylinder. So let's take a look at it. Take a look at that. Dump all of it down. Now you're seeing right here. Let's go. Seeing right here where the spikes are happening. These spikes are because the ferrofluid is actually going between the magnetic field of the cylinder that's attached to the neodymium magnets on the bottom. Now, it's spiking because the surface tension is holding it while the fluid wants to go with the magnetic field. That's why it's spiking up. But you can see right here in the middle as well. It's pretty cool.
Alright, since we did the cylindrical magnet, let's just now do the spherical magnet. And as you say,
Wow.
same thing, neodymium magnets on the bottom, and I'm gonna pour some of that. What's it called?
Ferrofluid.
Yeah, that thing.
Come on, man.
Install it off the top of the storage truck. Is that enough?
Look at that. Look how cool that looks.
Yeah.
And it's spiking because it's following the magnetic field coming out the cylinder. But it's also fighting the surface tension of the fluid.
Mm-hmm. So we're fighting. Now since we have a screw in there, we're just gonna try to see the magnetic field. And 3. Should I put it right now?
Yeah, go ahead.
Is that
You use all of it?
No.
Oh, that's so cool.
Yeah, it is.
Look at that.
You're not the one back there? Okay, so, hey,
Hey man, come on, man, get someone else, Namika. You go do it, man.
What's up, guys?
How's it going, guys?
How's it going, guys? Today, we'll be doing one of, no, I'm sorry.
How's it going,
There's
guys?
gonna be some outtakes.
You said one take, man. Don't go back.
Alright, let me get it right.
It's like you're
Alright,
saying on the
alright,
corner,
you're
make
crowding
it
me.
more
You guys
confident.
can't crowd me. I need to
I'm not crowding you. Mika,
okay.
let's come over here, man.
Why
are you zooming, man? We can do that with the computer.
Okay.
Don't do any like zooming.
What's up, guys? Today we'll be doing one of.
Are you guys recording? Say it when you're recording and say when you're not recording.
Alright.
So pause.
I'm gonna step in and then I'm gonna start.
Okay, you want to step in?
I'm gonna step in.
Alright, no, wait, we can do all that with the computer.